Hello all. So today we are going to continue from last lesson, conditional probability, and we are going to learn about Bayes theorem. So first we learn about the law of total probability, and then from there we develop the Bayes theorem. So let's say you have a partition, a BI, I equal 1 to 3, 1 to, it can be binary, it can be countable partition. Of sample space S. Then for an event A, we can write probability of event A equal sum of probability of A and BI. So let me draw this and explain you what this means. So you have partition of sample space. Okay. So this is S. Okay, so this is, let's say P1, B2, Bn, let's say it's a finite, okay? So now you have event A. It can be something like that. Okay, that's event A. Then this one is saying probability of event A is sum of these intersection. Okay. A and B1. So I can say BI. Okay, so this is A and B1. And if I use a different color, this would be A and B2. And for example, this would be A and Bn. Okay. So basically summation of A and Bi. So this is law of total probability. Now this one, probability A and Bi, you can rewrite using conditional probability. What is A and Bi? That's probability A given Bi time probability Bi. So this we call as law of total probability. So so Bayes theorem, it says, let's say you have a sample space S, which is partitioned into disjoint subset B1, B2, Bn, where S is sum of union IBI, which actually I should have included in here. Okay. And then Bi intersection Bj is empty. So then you have this nice rule. Okay. So first go with this part. That's of course that's, you can see it's true. Probability Bj given A. By definition of conditional probability, that's going to be probability Bj and A over probability of A. Now, the numerator part, of course, you can write using conditional probability time probability A given Bj. Okay. Just simplify and you will see that it's same as this one. Okay. Then the denominator from law of total probability, we just prove, we can say it's sum of I equal 1 to n probability Bi time probability A given Bi, which we just prove here. Okay. By the way, I should have said that this is union of these events going to be sample space. Bi intersection Bj is empty when I is not equal j, so forth. Otherwise, you can't really divide the sample space into the n partition, and this diagram is not true if B1 and B2 have common elements. So this is called as what we just proved. This is called as Bayes theorem. That's the Bayes theorem. So it's very useful when we calculating probabilities, conditional probabilities. Let's do example problem. So this one says an auto insurance company insures driver of all ages and actually compile the following statistic on the company insured driver. So you have 16 to 20, 21 to 30, all the way up to 99 years old. then the probability of accident, portion of company insured drivers. So question says a randomly selected driver that the company insure has an accident. Okay. Then calculate the probability that the driver was age 16 to 20. So you can see that this is partition of sample space. All the drivers you can always divide into this one of these age group. Okay. So 16 to 20, and they're not going to be any intersection. Okay. So then the event is actually company insurer has an accident. And an accident. So let's say this is A. Okay, this is B1, this is B2, B3, B4. So the question is saying, okay, if you know that driver had accident, what's the probability that driver was age 16 to 22, 16 to 20, so B1. What's that probability? Okay. So usual approach, when you have this, you write the Bayes theorem. So what is this? This is basically you change the order. So A given B1. If you check the Bayes theorem, you will see this. Okay. Then you write the sum. And actually we have partitioned into four subsets. So now we need to calculate these probabilities. So what's the probability of being in each group? So you can see that this is probability of B1. This is probability of B2. And this is probability of B3. And this is probability of B4. Now, if it is a true partition, when you add all this, you should get 1. Okay. Check whether that's going to happen. Okay, so so we know these probabilities. Okay, then what about this conditional probability, like B probability of occurring accident given B1? So that's this one. Okay, so this is one. This is probability A given B1, and the second one is actually probability of accident given B2. Okay. So now we have all the numbers we need. So the first one is 0.06 time 0.08. And then the rest is just a modification. I mean, they just do the same thing, but for the all 4 rows. If you look at this as rows, you can see I'm just modifying those numbers. Okay, so simplify it and get the answer. And you can comment more in detail. So here you can see another example. So this one says company issues life insurance policies in 3 separate categories. Okay, so you have your sample space divided into 3 categories. One is standard, and then the other one is preferred, and the other one is ultra preferred. So of the company's policyholder, 50% are standard. So the probability of being standard is 50%, and the probability of being preferred is 40%, and probability of being ultra preferred is 10%. Each standard policyholder has probability of 0.01 of dying in the next year. So if you know that the person from standard policy, then the probability of death is 0.01, If it is from preferred, then the probability of death is going to be 0.05. And then this one, if you know that ultra preferred, then the death is going to be 0.001. So policyholder dies in the next year. So given that death, they want to know disease from ultra preferred. So we can start from, we can use the Bayes theorem. So you change the order, death given ultra preferred, probability of ultra preferred, and then you sum up across all the partition. And probability of ultra preferred. So all these values are given, so you can just substitute. For example, plus 1 is 1. 0.005. Probability of ultra preferred is 0.001. Sorry. And probability of ultra preferred is 0.1. And then this one is 0.01 and 0.05 plus 0.005 times 0.4 plus then 0.001 and 0.1. You can simplify. So I leave the other problems for you to try, and then if you don't know how to do it, or if you are struggling, please come back to the module 3 discussion board and post it there, and then every one of us can comments and make a good discussion about those problems. Thank you.